Yes, okay. Okay, thank you very much for your works, and now we will start. As Marcio mentioned, we have only the talk for Mauricio, the professor, because for the time, because we need to 10 minutes to make presentation about the seminars. So Mauricio, okay, Mauricio is sharing. Thank you very much, and I will present him. Mauricio is professor and researcher in the Department of Computing at the School of Engineering and Science of Technology de Monterrey, Mexico. He graduated in electronics engineering from Francisco de Paula Santander University in Cúcuta, Colombia. He received a master's degree in electronic system from the Tecnológico de Monterrey, Mexico, and master in science and PhD degree in biomedical engineering from the University of Zaragoza in Spain. He leads the Neurotechnology and Brain-Computer Interface Research Lab, where he works in the field of brain-machine interface, bioelectronic and signal processing, brain imaging, decoding of cognitive states from electrophysiological recording, and instrumentation and data acquisition. In addition, he is a member of Gravitational Wave Data Analysis Group, where he oversees computational statistics and artificial intelligence techniques for the search, detection, and characterization of gravitational wave from different astrophysical sources, such as supernovae. As you see, the background of Mauricio is interesting because he can work with brain computer and gravitational wave because and that analysis led it. We have a very good collaboration with Mauricio. Okay, Mauricio, thank you very much for the opportunity to give these first seminars, and then go ahead, please.
Hello, everyone. Thank you very much. Claudia, can you confirm if you can hear me?
Yes, hear and
Yes.
see very well.
Okay, thank you. Hello, everyone. So thank you for the introduction, Claudia, and thank you for the organizers of this seminar series. Today, I'm going to talk about how to search for gravitational waves from core collapse supernovae using data from the LIGO, Virgo, and Cagra detectors. Indeed, those are part of the activities I do with Claudia and other collaborators here in Mexico. Let me introduce first our group. Basically, we are a group working in gravitation and data analysis for gravitational waves. There are professors and students in two universities, Tecnológico de Monterrey, Campus Guadalajara, and University of Guadalajara. So we are a, let's say, multidisciplinary team because in the physics department at the University of Guadalajara, where Claudia is the PI of the group, they oversees all the theory, all the fundamentals, all the basis about gravitational waves. And Tecnológico de Monterrey, we work more with algorithms, with data analysis, and we work together for this beautiful field of gravitational waves. So, with no more introduction, I want to start just highlighting that we are living in the era of gravitational waves astronomy. These gravitational waves, as you might know, are oscillations in the space-times that are produced by astrophysical objects, such as binary holes, neutron stars, objects that collide and merge, and during this process, they produce gravitational signals. Those signals travel through space-time and they reached Earth. So detectors as the LIGO, Virgo, and Cagra network are used to detect, to observe those tiny oscillations in the space-time. So you might also know that there are gravitational waves that have been detected so far, specifically gravitational waves produced by binary black holes and by binary neutron stars. One characteristic in these objects is that we can produce accurate signal models. I would say almost analytical signal models about these gravitational waves. And therefore, we can use algorithms as the matched filter to search for those gravitational signals. So we can find a recent catalog of gravitational wave transients in the Gravitational Waves Open Science Center. I think there are more than 200 gravitational waves detected so far. And indeed, this is a very recent image. I think it's from today, at least. It was shared in the group, in our group today. This is a matrix which shows the first detection here, GW uh, 25, 15, sorry, 07, 14. Here is the first gravitational wave detected. These are time frequency representations of the detected signals, starting from the first ones. They all are from binary systems that are orbiting each other uh, towards merger, producing a chirp type gravitational wave activity waveform. Um, it's important to mention, or interesting, at least to me, that al-
Yeah.
although there are much more neutron stars in the universe than black holes, most of these detections are from binary black mergers. And the reason is basically because black holes are heavier and are louder than the signals produced by neutron stars. Um, However, there are other sources of gravitational waves. Particularly in our group, we are interested in boson stars and also in these exotic astrophysical objects, Corcolab supernovae. They have been detected by humans, directly by humans, and the uh, last supernovae in the Milky Way was or occurred 300 years ago. And interestingly, the last remarkable supernovae in our vicinity, in the vicinity of the Milky Way, was 30 years ago. Um, it's im- I want to say also that these astrophysical sources, they have highly complex mechanisms. Um, and they are of interest because they are emitters of multi-messenger activity, electromagnetic signals, neutrinos, and also gravitational waves. They have been observed in the electromagnetic spectrum, and there is one observation of neutrinos from Corcolab supernovae. So here a little bit more about this multi-messenger activity provided by these interesting objects. So the scientific community says that this is the next frontier in the multi-messenger astrophysics because we will be able to observe electromagnetic signals, neutrinos, and gravitational waves. However, gravitational waves have not been detected yet. Just to finalize this brief introduction about gravitational waves, particularly from CCSN, so there are scientists working in how to calculate these gravitational signals, and they use multidimensional simulations to obtain characteristics waveforms. And those waveforms, they have these features. They are mostly stochastic. They are short duration, broadband, and with high frequency components. And from those simulations and from the obtained signals, we can compute time frequency representations where we can obtain physical information about the source, the supernovae. It is possible to observe in the time frequency activity the core bounds, SASI components, memory, high frequency features, and other physics related information uh, from the source. However, the search of these signals is really difficult. As I mentioned, they are mostly stochastic, so it is not possible to use uh, algorithms as the budget filter used for binary systems. So we need to use unmodeled based algorithms with minimum assumptions. So there is a pipeline to do so, coherent waveforms. I'm going to talk about it a little bit more later. So this is let's say, a general introduction. So my goal now is to show you two recent publications. One of them, this first from a small team, and the other one, the second one, from the LBK collaboration, where they did or they searched for gravitational waves, particularly specifically from Corcolab supernovae. So that's the idea now in the next slides. So this search was carried out in the third observing run of the advanced LIGO and an advanced Virgo. And the idea is to do a optically targeted search. And the reason is because when we have prior information about the supernovae. So this is the first task, indeed, to obtain or to select candidate supernovae where we can search for gravitational waves. So during the third observing run, astronomers found and followed several Corcolab supernovae in the nearby universe. Based on those detected supernovae, based on telegrams and on catalogs, the working team in this publication selected 8 supernovae to carry out the set of gravitational waves in those time windows. Here we have an example, supernovae 2019 EJJ is a type 2 supernovae. Here is the host galaxy. The estimated distance, which is the estimated distance of the galaxy, is almost 16 megaparsecs. And with the astrophysical information, we can compute then the so-called on-source window. That is the time segment where we can search for gravitational waves. The duration is almost 8 days, and the coincident days between detectors is 1.25 days. So in those 1.25 days we are going to search for gravitational waves on that period of time. So the inclusion criteria for selecting this supernovae was basically that the distance was lower than 30 megaparsecs, and also that we have a sufficient period of time in order to be able to search for gravitational waves. with sufficient data coverage to do the search. For those supernova, here we have the sky locations, which are known because the astronomers uh, provide uh, that that information. So again, the host galaxy is identified for all of them. So the sky locations are known, and this facilitates, at least a little bit, the search for gravitational waves. And that's why we can do targeted searches. So here is the on-source window, which is basically the time interval where we search for gravitational wave transients. This time window is the time interval containing the core bounce, basically the explosion of the supernovae, and a time period, a time segment that we consider that has gravitational wave emission. This visual representation basically shows the data coverage for in each detector, blue and red, for each supernovae. As we can see, there are other or some supernovae where the data coverage, the onshore window, it is small, and there are others when we have plenty of a bigger time segment to do the search. So the search is carried out or based on this algorithm, coherent waveforms, CWB. As I mentioned, it's a model independent search. We don't know, we don't need to provide to the algorithm a signature, a waveform that we want to look for. Um, the algorithm is based on wavelets and power excess analysis, and also in coincident tests. Basically, it aims to find the same activity in the same detectors to provide a, a wavelet or a time frequency representation for a detected signal. So it means that it is able also to reconstruct detected signals. So this is the algorithm used by the LBK collaboration in many of the search campaigns, and it was used here in this analysis. Now, I'm going to show you the search results. This figure shows the time frequency map of the most significant candidate detected across all 8 supernovae. It is a signal of duration about 4 seconds. It is a narrow band signal, as we can see here in the y-axis. The peak or the central frequency, it's about 835 hertz. The statistical analysis of these events gave a false alarm probability of 0.54 mm, in percentage, so which is equivalent to 2.8 sigma. So this is basically a high false alarm probability. And additional analysis on the data quality around this detected around this candidate shows that in the auxiliary channels there was a noise activity at the same frequency, very close the same frequency in the LIGO Hanford detectors. So the conclusion is to roll out this event to be of instrumental origin. I just want to recall to highlight that this was the most significant, the loudest event, and the conclusion is that it is of instrumental origin. So here we have also the loudest event for the rest of analyzed supernovae. As we can see, the false alarm probability is even higher for all those events. Sorry, supernovae. So the conclusion, though all of those events candidates triggers, sorry, are noise events. Sadly, the conclusion here in this first analysis is that no gravitational wave signals were detected in all those eight selected supernovae. However, we or the working team continue working on this supernovae, and they did a detection efficiency analysis where they basically calculated the sensitivity for different gravitational wave signals computed from simulations. So basically, the idea is to obtain gravitational wave signals freely available, produced by numerical scientists, and using, for instance, neutrino-driven explosions, black hole formations, and other physics-related activity. Indeed, it is possible to use also phenomenological gravitational wave signals. The idea is to add those signals many times to the detector strain data, and then to search for those gravitational waves signals, using, in this case, again, CWB. And this is repeated several times for different distances, so we can compute efficiency. That means uh, basically detection efficiency versus distance. Just as a quick example, we have here one of the models used to be injected in the strain data, and here is an example of how a gravitational wave signal from a supernova looks like. So here are the results of this detection efficiency analysis. We have the efficiency uh, versus distance for each of the multidimensional gravitational wave signals, and for each of the phenomenological signals. These vertical lines here represents the galactic center, and this is called Large Magellanic Cloud. Those vertical lines represent those systems. So basically, this figures shows that as the distance increases, the detection efficiency decreases. So we can compute for each of those models uh, the, the distance at which we reach, for instance, the 50% of efficiency, and we can analyze that. Sorry, I didn't mention, but these results are only for supernovae 2019 EJJ. This is also compute for all of the remaining supernovae time windows. Here is a summary of those detection efficiencies at 50%. So they found that the supernovae 2020 CXD is the one at which it is possible to reach greater distances or detectability in other words. So this is a summary of this work. They basically search for gravitational waves from already detected by astronomers supernovae. This is a targeted search, and for this search, a supernovae were selected, all within a maximum distance of 30 megaparsecs. So the conclusion is that no gravitational wave signals were detected, and the sensitivity analysis, sorry for the typo, indicated that the 50% detection efficiency did not reach beyond the Milky Way for those used models here. So I think that I have a couple of more minutes. I'm going to present you this more recent work. It is also devoted to the set of gravitational waves, but only for a specific supernovae, 2023 IXF. Um, it was discovered 3 years ago. The LBK detectors were operating in the so-called engineering run. They were taking data during the time this supernovae was detected. So astronomers provided the host galaxy, the sky location, the distance of the host galaxy, and the classification of supernovae. So with that information from the telegrams and from the catalogs, so we analyzed the data from the detectors. In this case, only data from Livingston and from Hanford. Uh, we can see here the coincidence between the detectors in the on-source window for this supernovae, which was calculated from photometric data as showing here. So using the photometric data, we calculated the on-source window, and then we go to the available data from the interferometers to check for coincidence and to search for gravitational waves there. Again, for the search, we use an improved version of CWB, which includes a classification uh, analysis based on XGBoost, which helps to discriminate between noise and uh, and discriminate noise events. Sorry. So for this search, the event, the candidate with the lowest false alarm probability was 75 percent. And basically, with this high probability, indicates that noise alone produces that trigger. The conclusion again is that no gravitational wave associated with this supernovae was identified or detected. The next is to do again the detection efficiency analysis, where we selected several existing gravitational waves signals from multidimensional simulations. We also used phenomenological emission models. And here we have again the detection efficiency results for those gravitational waves, which this analysis helps again to constrain the reach distance for each specific model. I'm going to switch to the summary of this work. So basically, during the uh, engineering run 15, the supernovae 2023 ISF was observed and followed by the astronomers. So we used that data to search for gravitational waves. Sadly, again, no significant candidate was accepted as gravitational wave. So these are two examples of how to search for gravitational waves from a specific astrophysical objects. In this case, Corcolab supernovae. So I just want to finalize my intervention saying that gravitational waves from compact binary systems are detected in a regular basis, I will say that. However, gravitational waves from other different astrophysical objects, including CCNS, SN, are still undetected. It is expected that gravitational waves, it is harder. They are harder to detect because they are weaker than those produced by binary mergers. Um, and also, it is important to mention this realistic point here that the most likely opportunity to detect a gravitational wave from supernovae is a galactic one, is when a galactic supernovae occurs. However, it is expected that the rate of a supernovae is in the order of 1 or 2 per century in the galaxy. Uh, so, yes, that's my presentation. Thank you very much. I don't know if we have time for questions. Thank you.
Yes, sure. We have time for questions, for question and more. Uh, Thank you, Mauricio. Okay, we start with the question. Is any have question? We can.
Hi, Mauricio. This is Reinaldo. May I ask one question, Claudio, to Mauricio?
Yes, of course, sure.
Yeah. Okay. I'm not my first expertise is not a gravitational wave. So sorry if my question is a little bit nonsense. But if you take into account the core collapse supernova as a transient, I was expecting to see some light curves from that, And my question is, the light curve pattern for core collapse supernova has some even in a fine-tuned difference of this kind of pattern comparing to the other transients.
Yes, I believe so. If I understood correctly, Albert, is that the light curve of this supernovae, it has different information in comparison with other objects, right? So is that correct? Just to make sure.
Yes. The question is the following: we are working right now in a software machine learning tool. The name is SurfT. We are doing a very huge classification with more than 85 different patterns for transient classes.
Mhm.
I realized that we still don't have any light curve for core collapse supernova. So we'll be. So I'm very interested to know if the increasing time, the peak time, and decreasing time, and also some small fluctuations for this transient has any particular pattern detail that put this in a different way from the other kinds of common transients? That's my
Ye-
question.
I think it's an interesting question. In general, to be honest, I don't know how to address the response to that. But what I have observed working with the light curve on many supernovae, I don't have information here about it. I only have this light curve. Is that, as you mentioned, yeah, there are fluctuations. I don't know because I don't have the experience, the expertise. I don't know whether they are noisy observations or they are giving information about something happening in the sky, I mean in the during the explosion. I don't know that the physical or the explanation for those fluctuations, but they are there. For this supernovae, it was the light curve was really clean. That's one of the reasons we wanted to analyze, because with that clean information we can compute the on-source window, so we can do a more reliable search and sensitivity analysis. So yeah, I know that that's an issue. That's an issue, and as you say, the machine learning is a good
Okay.
tool to help with
Okay.
solving those problems.
Okay, Javier. Thank you.
So
Just
sorry, if, yeah,
one
yeah.
more technical question.
Yeah.
You have mentioned in your abstract that you have been using machine learning, deep learning too. Could you
Yes.
specify which kind of models are you are based on? Your nice deep learning, machine learning, which kind of
Yeah,
models?
thank you. Thank you, Albert, for that question. I removed those slides from the presentations in order to save time. So let me give you a quick summary of some of the projects we have been doing with machine learning, deep learning. For instance, we have been working with CNNs in order to have very fast detections algorithms for binary black holes for the detection of gravitational wave from BBH. So we have used freely available data. We have we trained algorithms, and we then evaluate efficiency. So that's one type work type that we do here. For instance, we also use classical, I would say, classical machine learning algorithms, super vector machines, linear discriminant analysis, multi-layer perceptrons, in order to solve specific particular problems during a search. For instance, using CWB, we have this efficiency analysis I mentioned before. So we have noise triggers, signal triggers provided by CWB. So we
Ну,
use,
сейчас кончается, помню, же вопросы идут.
sorry, there is a mic open there. So we use supervised classification here, basically a classifier in order to remove noise triggers while keeping as maximum as possible signal triggers. And the idea of machine learning here is to improve the false alarm probability, to reduce the false alarm rate while maintaining the detection efficiency. So this is another example of how we use machine learning. Here we have another, not this one, but this one we have, oops, no, this one. We have also used deep learning, a regression model based on deep learning in a deep learning architecture to estimate parameters from detected gravitational waves from supernovae. And in this case, the model is tuned for detecting, for inferring, for estimating the slope of the so-called G mode or high frequency fissure. And finally, this one, we have also worked with multi-channel convolutional neural networks for detecting gravitational waves. And the idea is to deal automatically when one of the detectors fails and to have a model that continues working. So that's a quick summary, Albert. Thank you for the question.
Thank you, Javier. That's a nice piece of work. Thank you very much. I have many technical questions, but I will avoid here so we can keep in touch. So I will ask you, send you an email.
Yeah, definitely. Thank you.
Okay, thank you, Reynaldo. Now, Albert, please.
Well, my question is
Okay.
as follows. Did you try to use your scheme for testing possibilities? Do you suggest to use your scheme for testing possibilities of possible deviations from general relativity, that is modified gravity, something like this? Do you expect that some such testings will be possible?
First of all, sorry, Rinaldo and Albert. I think I switched your names. Um, oops. To be honest, I don't know how to answer that. I think it's more related with the physics, right? Or not?
Yeah.
Yeah. Oof. I, to, I'm going to be honest. I don't know how to answer the question. I think it's really, really critical, important, but no my expertise. It is not my expertise. So sorry for that. If someone in the audience can provide any comments, I really appreciate it.
Can I make
So,
a comment about that?
yes, please go ahead. Thank you.
It's just an idea. Maybe we could use CWB to try to search for extra polarization states of gravitational waves, because in alternative theories of gravity, we have like scalar polarization modes or vector modes. Maybe the code could be adapted to search for those modes. If we have a core collapse supernova, for instance, that modes would be produced in these other theories of gravity. Maybe that could be an opportunity to test gravity.
Yeah, excellent answer.
Yeah, thank you for that. Thank you. Yeah, I think we have more questions.
Julio, please go ahead.
Yes.
Thank you, Javier, for the nice presentation. I have two short questions. The first one, for the first search that you mentioned for your presentation, you use, like, I know that CWP has some boosts from certain types of morphologies. The search use a certain type of boost, a booster to search for example, like a ring down shape or something like that. I know that CWP doesn't look for specific waveforms, but there's a setup for that, right? I'm just wondering if
Yes.
search uses a certain type of boost on that.
Yes, Julio, definitely. Yeah. This is let's say a specific parameterized version of the algorithm of the method for short transients and broadband signals. So yes, it has to be tuned for that particular search.
Yeah, but for example, do you implement some kind of for in the time frequency domain, the wavelet map for a certain type of shape, certain type of morphology, the algorithm is modified to have a preference on that kind of to select those kind of pixels or something like that, or is the default version of CWP?
Well, it is parameterized. Is the default, but parameterized for short transients, short duration transients, and broadband. Don't remember now the lowest frequency. I will say 100 hertz up to 2000 hertz. So yeah, that's something that we need to include there in the parameter of the method at the beginning, the user parameters. Yeah.
Okay, thank you. And the second one was about the the simulation analysis. You were able to constrain a certain type of physical parameters of the core collapse supernovas with the simulations, like the energy of the supernovas, or the isotropic energy, or another type
Yes.
of parameter.
Yes, definitely. Those were part of the analysis in the detection of efficiency, the energy constraints, for instance. Yeah, that's part of the work. I don't have it here in the slides, but they are there in the manuscript. Yeah, definitely.
Great, thank you.
Okay.
Thank you. Go ahead, Antonio, please.
Hi, Javier, thank you for the presentation. My question is regarding the cosmological information.
Sorry, Mauricio, can you mute, please? Okay, Antonio, again, please.
So regarding the cosmological information that can be gained from this kind of event. So you were mentioning that this is the hope of observing any of these gravitational waves is mostly for galaxies. So for third generation detectors like Astronomy telescopes or Cosmic Explorer, what is an equivalent estimation? Basically, up to what redshift it is expected we could observe this, because this would be very good for cosmology, because supernovae are the brightest objects we can observe and determine accurately the redshift of. And so if we could also measure gravitational waves from these objects, it would be very good for estimating cosmological parameter. Thank you.
Thank you, Antonio. Okay, thank you.
Sorry, I was muted.
Okay. Okay, thank you, Mauricio. If there is no question, I have you're a student Josian can give a presentation, Mauricio. It's only 5-10 minutes in order to have a student. You agree, Mauricio?
Yes, if he's ready.
Yes, he is ready.
Fantastic.
Yes. And now we will have a presentation by Josian he's a student from Mauricio Antelis, and then Josian, please go ahead.
Okay, thank you. Can you see my screen?
Almost.
Yes.
Okay. Yes.
Great, thank you. Well, I'm going to present you my research, which is related with using machine learning models to
Josian,
generate signals.
Josian, sorry, before was good for see the presentation, and maybe it's not for full screen.
To up the configuration.
Yes, I think right now you can see correctly. Or
Yes, yes.
Great, thank you. Well, I'm going to present you my research, which is related with using machine learning models to generate signals from gravitational waves from core collapse supernovae. Well, first of all, and the reason of this research is based on the data sparsity that is in the field of core collapse supernovae, because as we saw in Mauricio presentations, the nature of this kind of signals is mostly stochastic, so it's difficult to generate numerically this kind of waveforms. So there are many, but there are two main, and I would say principal data sets of these waveforms, which is the Richards et al. And the Abikairab et al. So, and we use this, and specifically the Richards et al. Dataset to train a machine learning model and to generate these kind of signals and in a quickly way. So, well, some of the previous work very quickly, and there has been first of all, there is a machine learning architecture which is called generative adversarial networks, and these models are used to generate images, but also can be used to generate signals. And previously, these models have been used to generate signals from concurrent supernovae, but without control of the astrophysical conditional parameters. So, for example, we can see here in this plot that we have several waveforms with different morphologies, and it is well known that a parameter which we call beta, is related with the amplitude of the core at bounds. So we will expect that by controlling this beta parameter in the generative adversarial network, we will generate signals according to this parameter. So it will be in this work, and the authors didn't do that, just generate general these kind of signals, but without control of the astrophysical parameters. And there is a recent improvement in these models, which is called a CDB GAN, which only in a very general way, only includes derivative feedback in the discriminators, and also uses a auxiliary discriminator. But the great thing of this work is that we have now a way to condition the signals that are going to be generated. So this work was actually used for generate gravitational waves, but not for core collapse supernovae. It was used for generate signals from binary, specifically for CBCs, for example, for the binary black hole merge, and for some glitches, as we can see in the plot in the right hand. So our purpose was to use this architecture, adapt the architecture to use the signals from the Richards et al. Catalog and generate signals with conditional parameters. So we can see some previous results. We used the Richards et al. Catalog, which we divided the the catalog using one parameter, which is the beta parameter, and we extract five um, classes, and also we augmented this data set because we can see that there is an unbalance here. We augmented and we trained the generative adversarial network to generate signals from this controlling this beta parameter. So we can see in the preliminary results that actually the higher the beta parameter class, the higher also the amplitude at the core bounds, which is a clear representation of the of that the generated adversarial network is learning correctly the morphology of each class according to this parameter. So we also evaluated numerically and statistically these generations, and we have seen some results very quickly. We can see that there is a high relation between the generated and the training data set, and also we can see that the MMD, maximum mean discrepancy analysis, show that for cross classes, for example, if we compare the class 1 with the class 5, we wouldn't expect that there is a higher correlation, and this is in fact the results here. We have approved that the different classes are separated in the statistical space. So this will be all for my talk. Thank you.
Thank you, Josian. If someone has a question.
I have a question for Josiane.
Okay, go ahead.
Josiane, two quick questions. Can you show your slide number 4 again, please?
Yes. Sorry. Is this one?
Number 4. I think that's number 5. Yeah, this one. You are showing many, let's say, profiles, but you are looking for a target, let's say, like that. And when you see the profile on the top on the right, it seems to me a very interesting target for the gravitational wave pattern, right? How
right. Well, you
are looking for...
Sorry.
Yes, go ahead.
These signals that we can see in this plot are actually generated signals by the machine learning model presented in this slide.
Yeah, but this is from generative AI, or how?
Yes, these signals are generated, and specifically we would like to see just the vertex amplitude, which is the for example, we can see here that in the one with the 100 is, for example, for a specific kind of glitch, and for the third is for a CBC merge.
Okay, because my question is because I'm very concerning the problem that when you use a Gen AI, you need also to define a pipeline for XAI, explainable AI. You need to be able to interpret how AI is generating your data. And when you do that, usually we need to have a target. You can say, I can optimize my outputs and say, the best one, the target is the following. I can have 1, 2, or 3. So you can interpret the performance of your generative AI based on those targets. So that's my question. Are you taking care of this XAI approach on your data generative tool?
Yes. Right now, I think I don't. I just I didn't try to explain, but not to explain, but to use this kind of tool that you're talking about. I just evaluated by comparing with the original data set.
Right. Okay. Actually, the output of your analysis is just, let's say, confusion matrix at the final, right? So you can, let's say, quantify the performance of this generative AI. That's okay. But I'm just asking you about that because nowadays we are trying to use, when you are using especially generative AI, you bring it to the pipeline layer where you can see which kind of interpretability or explainability, that's what we call XAI, we are using on. That's very important. Just one point that we should discuss sometime.
Sure. Maybe I could do that since I am working with deep learning, and maybe just to see at the feature maps generated well constructed by the network, and see what characteristics or what patterns we can extract for them.
Thank you. Yeah, as you mentioned, deep learning also is very important. One kind of explainability that's very important is when you are doing the validation, training and validation for such deep learning model. For example, how you choose the hyperparameters when you are training the machine learning or deep learning model. That's also is very important to explicit in the approach. That's just one very important concern also. For example, people use Optuna, a framework that helps you to choose the best hyperparameter set. So that's one example, okay? But let's keep in touch. That your work is very important. It's very well. Thank you.
Thank you to you, Reynaldo, for your questions. Okay. Okay, I think we finished our first seminar. Thank you very much to Javier and Joshua for his talk, and I hope to be in touch with. You have our email site? No, I don't have. I will look for a communication between us in some time.
Can you hear me?
Yes.
So I don't think I got the answer to my question. Maybe I missed it, but I asked a question.
Yes.
Sure.
Yes, Antonio, sorry for that.
No, it's okay. I thought I had a technical problem, and then I. If it is too long, it's okay. We can end here. I just thought.
No. It's okay for us. If
yes,
I think
if you can repeat again, please, the comment.
Okay, sure. Very quickly. So basically, what is the prospect of observing these gravitational waves for extragalactic, core collapse supernovae in the future? Because from what I understand, our hope is very low for the present detectors. But what about the third generation? How far could we detect this?
Yeah, I think that there will be more possibilities on that with these future detectors. Indeed, we have analyzed the sensitivity of those detectors for considering only the quasi-deterministic core bounce component of gravitational wave signal from supernovae. So it seems to be much more possible or more reachable to detect these gravitational waves. So it means that we also need to push forward on that science, which will be really important for the supernovae field. I know also that there are people working in the low frequency sensitivity, improving the low frequency sensitivity of the current LIGO, Virgo, and Cagra detectors. But in any case, the possibilities are higher with these future detectors you are mentioning.
Okay. So how far can you go? Did anybody estimate it, like redshift 1, or I don't know? Okay. Okay. Thank you.
Yeah. Thank you.
Just a comment. Yes, there are so much expectations to detect supernovae, but we have many problems like the distance because it's one in our galaxy, and we are considering 10 kiloparsecs, and maybe the events are far over that distance. But we are trying, and I think so. We are not sure about the expectation in the future, but we are working on that. Okay. Okay. Thank you, Antonio. Okay, if there is something else, Odilio or Marcio, Antonio.
Just to advertise the next seminar, it will be given by Odilio. Odilio will be the next speaker on April 6th of April. 16, sorry, 16th of April. Odilio will give the next seminar about a way to cool down to 123 Kelvin, the test masses of an interferometer. Is right, Odilio? You are muted.
Marcio, it's correct. Yeah. Thank you.
Okay, so we hope to see all of you there next month.
Thank you very much for organizing it.
Are we going to meet after this meeting, or is no longer necessary?